Good afternoon and welcome to today's HydroCAD webinar. Today's topic will be rainfall distributions and unit hydrographs and how they play into the runoff calculations that are being performed by HydroCAD. Before we get started, during this session you can use either your telephone or your computer audio. If you want to free up your landline and just use the computer, you can do that. Your microphone will be muted for the duration of the session, so if you just have speakers, that will work fine. For any questions or comments you may have as we go along, please use either the question box or the chat box, and you'll find those in your GoToWebinar control panel. You can expand those sections if you want to, and just use those for any questions. We'll either try to deal with the questions as we go along or at the end. My name is Peter Smart, and I'm going to be the presenter for this afternoon's session. And to start out, I just want to talk a little bit about rainfall distributions and what they are. There are often misunderstandings about exactly what a rainfall distribution is and perhaps how it compares to an IDF curve. The screen that we have up here is a HydroCAD report screen for rainfall distributions showing the common type 1, 1A, and 2 rainfall distributions which are used in much of the United States. And the nature of a rainfall distribution is that these are actually synthetic storms which are intended to represent a synthetic distribution of rainfall over a certain period of time. They're typically a 24-hour duration. And so this will tell us at 1 hour, 2 hours, 3, 4, 5, etc., how much rain has fallen at that point within a 24-hour storm. This is different from an IDF curve, which is intended to tell us the intensity of rainfall that will fall for a given duration event. So, for example, an IDF curve would tell us that in a 1 hour event we might get 1.5 inches of rainfall. The rainfall distributions are temporal distributions. They're somewhat different animal. And they're typically represented by a mass curve, as you see here. And this indicates the fraction of the total rainfall depth which has fallen at any point in time. This is why they're often called dimensionless rainfall distributions, because there's an axis of 0 to 1. They are not yet dimensioned with the actual local rainfall depth. As for the 0 to 24 hour scale, why are they scaled to 24 hours? This is somewhat arbitrary, but it's a convention that's been established to use a 24-hour rainfall for studying events on the majority of sites. The 24-hour rainfall includes rainfall data for all shorter duration events, and that's a very important aspect of the synthetic distributions and the SCS method in general. So by using this one 24-hour rainfall distribution, we're actually including all of the shorter events. So we're looking at the 3-hour, the 6-hour, the 12-hour event. They're all included within that one distribution. So for most studies, there's no need to use different durations of rainfall as you might have previously done with the rational method. With the SCS or NRCS method, you can use that one 24-hour duration. Are there cases where you might need to change the 24 hours? Sometimes this happens, but not very often. One scenario would be if you were looking at an especially large watershed that took longer than 24 hours to respond. Then, for example, if your TCs are quite long, if they're running tens of hours for your TCs, then you might want to use a longer duration storm, and you might go up to a 48-hour storm, perhaps. But that's quite rare. You have to be getting to quite a large watershed for that kind of study, and usually you're migrating to statistical techniques for doing that kind of watershed study, as opposed to the SCS NRCS procedure. Shorter durations are also a possibility, and they are becoming somewhat more common as we get into studying water quality events. If you're only looking at an inch of rainfall over the site, then it's more realistic to distribute that over 6 hours than it is over 24 hours. So we will be talking about some of the other storms durations that are available and how you might set those up. Another important aspect of the NRCS storms is the peak, and the peak duration for a Type 2 storm is set in the middle of the storm at the 12-hour mark. The Type 1 and 1A peaks are slightly earlier. And this is again somewhat arbitrary. With an actual storm, your peak may occur at most any time during the distribution, and it's not going to be a nice smooth curve. These are synthetic curves, meaning they're not actual observed storms. They're compiled from rainfall distributions nationwide and then used to produce this idealized event, which is designed to model all the different durations within this one distribution. You can also model an actual observed rainfall event. That's another possibility we'll talk about. If you have sufficient observed data, then it's possible to do that. Let's have a look for a minute if we start up HydroCAD, another very good way to view your rainfalls. You don't even need to have a project open in HydroCAD. You can just go to View Storm Distribution, and you'll find that on the new toolbar over on the right-hand side, or you can go to your top menu and you can do View Storm Distribution. They both take you to exactly the same place. And this screen shows you the storm distribution report, and the pane on the right-hand side shows you all of the rainfalls that you currently have installed with HydroCAD. Most of these are pre-installed, although there are some additional rainfalls that are available for download, as we'll talk about in a little while. And so way down the bottom of this list, you can see the NRCS distributions if we expand those. So here is the type 2 24-hour distribution, for example. The storm report has got a number of handy features in it. In addition to viewing the basic mass curve representation, we can also switch up top here to an intensity curve. So this is the derivative, the slope of the mass curve, and this shows us actual intensity versus time. And here it's easy to see how that peak has been located at the 12-hour mark in the middle of the storm. And of course you can resize this window in various ways. Another trick is that you can zoom in on any of these graphical reports. If you take your mouse and you drag from upper left to lower right and drag a selection rectangle and then release, it will zoom in over that part of the curve. So here we've just zoomed in on the peak. To reverse that zoom process or to undo it, just drag in the opposite direction from lower right to upper left. You may notice at the top of the storm distribution report there's a time increment box. This is the increment that's being used for the report that you're looking at. This is not the increment of the underlying rainfall distribution. That's a separate issue that we'll look at in a little while. This is just the sampling that's being used off that curve in order to generate the actual graph you're looking at. We can, of course, switch this to a tabular view as well, and here this is tabulated in the time increment that's shown up at the top of the graph. The box at the very top of this report is giving us summary information for the particular rainfall that we have selected. So in this case, it's telling us that this is the type 2 24-hour rainfall and that it's based on SCS coefficients. 18 polynomial coefficients are what are used to define this curve. The basic SCS distributions that are shipped with HydroCAD are polynomial based, and the intent of those is to provide you with a nice smooth continuous curve. If you use a tabular mass curve, which is another option, then you can get steps in the intensity function and even in the runoff, particularly as your time of concentration gets quite short. So you will find both of those different kinds of distributions are in use. There are, in fact, tabular versions of the NRCS rainfall distributions which are available to download from our website. They're not normally installed with HydroCAD, but you can download them if you need to. Why would you use them? The primary purpose would be if you were trying to replicate precisely a runoff study that had been done with TR20 or perhaps with some other program, then you might want to use the tabular distribution. We can select multiple storms here in order to compare them. So if I, in addition to the type 2, the standard coefficient based, if I pick the type 2 tabular, we now have two different storms that are being displayed. And you'll notice those curves lay exactly on top of each other. When viewed in this particular view with a 10th hour time increment, they're the same. And that's actually because the type 2 distribution, the tabular one, is internally generated at a 10th hour increment. And so when we sample at that time spacing, the two curves look the same. If we go to the depth curve, the mass curve, here you can see the two mass curves laid exactly on top of each other. let's go back to the intensity curve, and if we decrease the interval at which this is being sampled, perhaps down to 5/100ths of an hour, now you'll notice a slight difference is appearing between the type 2 coefficient-based storm, which is in red, and the green tabular hydrograph. This is because we're now sampling at half the time increment at which the tabular curve is actually created. So there's no additional time intensity data available for shorter events in the tabular table. It only has points at that 10th hour increment. But the coefficient-based curve is a continuous curve that actually has some data for shorter durations. And so as we go down here to a point of 5/100ths of an hour, you can see that the peak intensity from the coefficient-based curve is slightly higher. So that is an expected difference you may see, particularly as you get to very short TC values. It's usually not an issue, and using the standard built-in coefficient-based curves is what's normally recommended. But if you're doing a direct comparison to some other study, that's one of the reasons you may see differences. If you want to look at any of these rainfalls in detail, then you can just go to that particular curve and right-click and select Edit, or you could use the Edit button down the bottom. And that will open up an internal editor that will show you the actual details of that rainfall distribution. So this is the type 2 24-hour tabular, and these are the actual tabular depth values. So if you were to pull up your TR20 input file, these are the exact values you would see. And of course, you can use this capability to set up custom rainfall distributions. So if you have rainfall data for perhaps an observed storm or a study that someone else has done using a different rainfall definition, and you want to replicate that data, then you could set up a custom rainfall distribution. And if you come to this screen and click the Instructions button, you'll find full details on how these rainfall distribution files are defined and all of the options that are available. You can define mass curves, intensity curves. You can by either coefficients or by points. So there are a range of different options that are available in setting up these files. Looking briefly at the standard type 2 file, if we edit that, just so you can see what's happening internally, these are the coefficients. This is a third order polynomial, and these are the coefficients for each term in the polynomial. So we have coefficients that cover a certain time range. The first coefficient is from 0 to 4 hours, then the next coefficient set covers from 4 to 8, and then from 8 to 9. And as we get close to the peak, the segments get considerably shorter, from 11.5 to 11.75. So this gives us the nice smooth curve that you typically see when you're looking at the type 2 coefficient-based distribution. And even as we go quite short on that curve, we are always going to see a nice smooth result without any steps in it. If we were to look at the type 2 tabular, then you can see that the steps that are starting to develop here when we go down to a very small time increment. And this is because if we sample every 100th of an hour, we're actually taking 10 samples over each 10th hour increment that tabular storm is defined for. And so we're getting a constant intensity for those 10 samples, and that's why we have this little step that's showing up here on the graph. You'll notice this is 1/10th hour of duration. So just a little bit of background on different ways of defining rainfalls. You normally aren't going to run into this, but sometimes you may, and then you'll need to understand this background information. When you're using rainfalls in HydroCAD, let me open up a project here. We'll go to the Mountain View Housing Complex, which is an example that's pre-installed with HydroCAD. And if you go to your calculation settings, onto the Rainfall tab, this is where you would normally select your rainfall distribution. So here we've selected our type 2 24-hour rainfall, and of course you can select any of the rainfalls that are installed with HydroCAD, and this would include any additional rainfalls that you've downloaded and added yourself. And you can use the View Storm button on that same screen in order to bring us back to the same storm distribution report. It's just another way to get there. Along with the storm distribution that you select, you also have to pick a storm depth and duration. Now, this screen is laid out a little bit differently than what you're looking at. On your version of HydroCAD, this is actually a preview of what we're working on for the next HydroCAD 9.2 release, which is expected roughly at the end of the year. And this has been reorganized a little bit in order to accommodate some new capabilities for defining rainfall events. And we'll give you a sneak peek at that in a couple of minutes. But the critical information you have to define whenever you're picking a Type 2 storm is going to be the storm depth. So you need to tell the software how to scale that rainfall distribution. That depth, of course, is going to be different for each of your rainfall events. So rather than having to manually type in the rainfall depth every time it changes, you can define a set of rainfall events in HydroCAD. And there are a number of different ways of defining rainfall events, and that's what I want to go through. There are several options you already have, and then there are more options that will be coming in future releases. Let's cancel that for a minute and just open up a new sample project here. We'll just call this Webinar 203 for today's session. And just bring in a subcatchment so we have something on the screen. And you notice now with a new project, our event selector is blank. We have no events defined. So we need to go to Calculation Settings and to the Rainfall tab. And you can see in red that we have no depth. So we could just put in a 5-inch depth there. But then we would have to change the depth manually every time we define a new event. So to define our rainfall events, we have a number of different options. And I'm going to go through these essentially with the easiest or most preferred ones first. And if you excuse me just a second here, I want to close this Mountain View project because I'm actually going to import rainfall events from this project, and it needs to be closed when we do that. So if we come into our new project, back to the Rainfall tab of Calculation Settings, the first option for setting up your events, the easiest one is to use the Import button. If you use Import, this lets you select any other existing project which has already got rainfall data in it. So if you've already done a project for the particular site or area that you're looking at now, and that the rainfall data will be the same or similar, then you could pick that project. And when you do, it automatically imports all of the rainfall events from that other project into the current file. So each of these events now sets all of the parameters on this screen. So the 10-year event is specifying that it's a Type 2 24-hour storm with a depth of 3.7 inches. It's also setting these other parameters, which usually we leave at the default. The antecedent moisture condition is normally 2, and it's normally 1 back-to-back storm. Back-to-back storm setting is used to create multiple identical storms, and I can show you that briefly. Let's go into this subcatchment and edit this, and let's put in, just pick a curve number here, put in 10 acres, and I'm going to do a TC just with direct entry, just so this is quick. Let's put in 15 minutes for a TC, and now we can double-click the subcatchment to get a runoff hydrograph. So we're now looking at the runoff from a single storm. If we go back to Calculation Settings and we change that to 2 back-to-back storms and click OK, that's going to give us 24 hours with one storm and then 24 hours with a second storm. We click OK and come back to our hydrograph. Strange thing is it doesn't look any different. Well, that's because the second storm isn't starting until 24 hours. So in addition to setting the number of back-to-back storms, we also need to increase our calculation time span. So let's run that right out to 48 hours and click OK. And now on our hydrograph you can see we have 2 peaks for the 2 back-to-back storms. Now, those 2 back-to-back storms are identical, so why are the peaks different? It's because the first storm is satisfying, the first 24-hour interval is satisfying the initial abstraction in the SCS runoff equation. So when the second 24-hour storm hits, even though it's the identical rainfall depth, we get a much greater amount of runoff. So this is one of the many different runoff options you have available to you. The antecedent moisture condition is another one, and these are actually items that we'll be talking about in the next session, where we talk about curve numbers and TC effects in 2 weeks. That's essentially the second half of today's program, to talk about the other parameters that go into calculating your actual runoff hydrograph. So if we go back and reselect our 10-year event, then it will reset all of the fields on this form to the predefined 10-year settings, so our back-to-back storms has gone back to 1. So that was our first option for defining rainfall distributions, is to use the import button and bring them in from another project. If you have additional storms that you need to define, you can still do that, so you can modify them. So maybe on this site your 10-year depth is slightly different, so we could change our 10-year depth to 3.8 inches and then click Save, and it would ask us if we want to replace the 10-year event. So we've now started with imported events, but we've changed that 10-year event and put a slightly different depth in. We can also define additional events manually. So if we have a water quality event that we want to set up, we might put in 1 inch as our rainfall depth, and then come to the event name, and we could type in WQ for water quality, or whatever abbreviation you choose, and click Save. And now on our drop-down list, you can see we have all of the return periods plus the water quality event. And if we click OK, we get our reports updated, and there's our essentially zero runoff for 1 inch in this of rain in this particular case. But our rainfall event selector now has all the events plus the water quality storm. So there are other purposes you can use the event definition for. It's not strictly limited to the return periods, and you can have any number of definitions there. So this can include a 250, a 500-year event, whatever storm you may have, a maximum probable precipitation. Each of those can be defined as a separate event in this box. Now, your next option, if you don't have an existing project with events that are similar to the ones you want to use, let me just clear out all of these events, so that, and I'll close this window here just so it doesn't keep popping up on us. Go back to calculation settings. So the next option for defining your rainfall events is a lookup button. The lookup button will bring up a table of rainfall event definitions. These are the tables essentially that are used in Windows TR20 and Windows TR55. And this is an NRCS list which is organized by state and then by county. Some of this table you'll notice is blank because the NRCS has not produced these rainfall settings for all locations in the county, in this country rather. So if we scroll down here, you'll see that it is populated for most of the country. So if we come down to Kentucky, you could pick a particular county in Kentucky, and you can see the storm and the depths that are used at that location. So this is a very easy way now. This was added in HydroCAD 9.1, I believe. This is an easy way to come in and pick your exact location. And then you would just click the OK button, and that would define each of the rainfall events accordingly from that particular table. Now, you should check those values and make sure they're consistent with your local stormwater regulations or other sources. This is one snapshot, essentially, of nationwide rainfall data, and these values may change over time, and your regulations may have other settings. Nevertheless, it's a quick way to get your rainfall settings in, particularly on an initial project where you may not be able to import from another job that you've already done. On the lower left corner of the screen, there is a box where you can select the event lookup file. By default, this will select the pre-installed table, the NRCS rainfall table. But this box allows you to define custom lookup tables. So you could go into your HydroCAD rainfall folder, and you could actually make a copy of this NRCS rain file. And in my case, I've made a copy called My Rain, which I've gone in and edited the file. You'll see it's a fairly straightforward text file. And in this case, I've just pulled out a couple of states in the Northeast. So if you're just working in a limited area and you don't want to see all the blank lines for Alaska at the beginning of the list, then you can go in and customize it. And you could add additional regions that might be defined in your state, and you could customize the values for each of the return periods if yours happen to be different. And once you've created this custom file, that will not be disturbed when you install a subsequent HydroCAD update. It will only replace the NRCS rain file, which is why you don't want to customize that standard definition, because that is subject to being overwritten when an update is installed. So you should make a copy of that file and store that under a different name if you're going to create a customized lookup file. So that's the lookup capability based on a table by county. That's the next of several options. The next place you should look for rainfall distributions or rainfall information, if those don't work for you, is to go to the download page on our website. This page lists all of the standard rainfall tables that are installed with HydroCAD, and about half of the files on this table are pre-installed. However, this list also includes a number of rainfall distributions which are not pre-installed with HydroCAD. For example, we've got rainfalls here for Republic of South Africa in various different flavors. You will also find the NRCS tabular distributions here that I mentioned. So if you were doing a comparison to a calculation that was done using tabular rainfall, then you can come in here and you can download those specific rainfall distributions. We also have here, perhaps of most interest, rainfall distributions, NRCS distributions for 6 and 12-hour storms. These are now standardly installed with HydroCAD. I believe with HydroCAD 9.1 these storms are automatically installed. But you can download these and use them with earlier versions of the software as well. And these are here for specialized projects where you may need to use a shorter duration version of the NRCS rainfall distribution. So these are all available for download, these additional items that are hyperlinked, so you can come into this table and download additional files that may get posted over time. So this is your next resource for where you should check for rainfall information. The next option for defining rainfall events is something that's actually not available to you fully at the moment, and that is to take advantage of the NOAA rainfall data that is published online for specific locations. And this allows you, let me come into the NOAA site here, and you can actually pick, this is often called their precipitation frequency data server, you can pick a particular state and come in to a particular station within that state. You can pick that location, or you can pick an observing site by name. There are several different ways to do the selection. And it will then bring up, as long as the site's working, a number of options for the data that you can extract for that particular location. And it should have already come up. It didn't. All right, let's go back then instead. And there is a similar site which is being developed for the Northeast. One of the problems with the NOAA Precipitation Frequency Data Server is that it only covers part of the country where they've had contracts to actually develop the data, and that has very notably excluded the Northeast. There is a new website being developed by Cornell and other organizations which covers the Northeast. It's quite similar in operation to the NOAA site, and it lets us pick a point on a map, or we can select by location. So now we can actually get data for Middlesex, Connecticut, which is not otherwise available on the NOAA server, and we can select formats for that information, click the Submit button, and this will bring up a table. Essentially, IDF information is what we're pulling up here. It is the depth or the equivalent intensity of the rainfall that will occur for given durations and return periods. And one way you can use this is simply to determine your 24-hour rainfall depth. So here we have the depth for each of your 24-hour events. But the capability that you're going to see coming is that we will be able to actually generate rainfall distributions based on the NOAA data. So once we have downloaded one of these rainfalls from the site, and we will actually be able to view those either from the NOAA site or the Northeast site directly as an IDF curve in HydroCAD. You won't even need to convert that. We can treat that as a native IDF file. And here's a view of what that IDF curve looks like. But what's relevant here is that we'll also be able to convert that file to mass curves. So we can do a conversion process which is very similar to the process that NRCS used to develop the type 1, 1A, 2, and 3. And we can convert that local IDF data into a set of rainfall distributions, which are right here. It's just been converted. And again, this is something that's not going to be available to you directly until roughly the end of the year with the next release. But what we've done is we have created a separate mass curve for each of those return periods based on the IDF information for that particular site. And you'll notice that the curves are quite similar for each return period, but there can be subtle differences. And one of the neat things you can now do with this rainfall viewer is that we could look at the 10-year event for Everett, Pennsylvania, and we could superimpose that on top of the NRCS Type 2 storm. And you can see they're fairly similar. There are some differences. The differences will become more apparent when you switch to the intensity view. And here you can see that the custom distribution that we've just generated for local data is producing a peak that's about 10% higher than the Type 2 storm. Sometimes this local peak will be higher, sometimes it will be lower. There's no way to generalize except to say that there may be some differences. So one of the evolving things that we're seeing happening is starting to use local rainfall data and create custom rainfall distributions instead of using the standardized Type 1, 1A, 2, and 3 storms. As to how this is going to pan out in local regulations, no one knows at this stage. Right now, it's basically because we have this data available from the Precipitation Frequency Data Server, readily available, downloadable, the capability will be there that you can do this conversion on your own and create a local curve. But these curves are not perfect. For example, when you look at this curve closely, you'll see we've got these anomalies where we actually have a dip in the intensity. So this is not producing the nice, smooth, synthetic rainfall distribution that we're used to with a Type 2. So there are actually some smoothing options that are used. The latest Windows Tier 20 software has built in the capability to do this conversion, and they have a smoothing option which essentially discards intermediate points and uses a smaller number of IDF values in order to create the final rainfall distribution, in order to give you a smoother result that doesn't have these anomalies. So at this point, if you need to do this, what you can do is you can download the precipitation data for your particular project site, and if you email that to support@hydrocad.net, then we can do the conversion for you, and we can send you back standard rainfall distributions that you can use within your HydroCAD model. With the next release, as I say, you'll be able to do that conversion yourself. But this is still a capability that's under development, and we're looking at different smoothing options, and that will help us determine what options you want to use when we get to that final release. So that is our next option, is converting the NOAA data, and again, you'll be able to use that for IDF data if you were using rational method. We're certainly not encouraging that, but that would be available to you, or you can convert it and use it as a standard rainfall distribution with the NRCS procedure. Then the last option for creating rainfall distributions is actually to set up a custom distribution on your own. And this should be very rare that you need to do this. If you have a custom rainfall that's in your local stormwater regulations, then hopefully that's something we already have in HydroCAD. For example, we've already got distributions for Charlotte, North Carolina. They're 6-hour, 2-year, and 10-year storms. Those are already here. But if you do run into some other distribution that you find is not in the software, then you can define one of those yourselves. And the best way to do that is to go into one of the sample distributions. And there's a sample A, B, C, and D. And these are defined using the different options. A is an intensity curve example using points on the intensity curve. B is a mass curve example. C uses a smoothing option. and then D uses actually a Chicago-style storm, which is based on IDF coefficients. So depending on the kind of data you have available to you, you can pick one of those storms, click the Edit button, and then come in and essentially customize that file and store it under a new name in order to create a local rainfall distribution. So that's the last of the options. Essentially, that's your last recourse. But certainly contact us before you set up a custom rainfall, because it's very likely that we'll already have a distribution set up that you can use for that purpose. We did have a question that came in a little while ago. Someone asked why the default time span for the 24-hour event was set to 5 to 20 hours. The reason, let me just open this up again, because we've now changed this from 5 to 48. Let's come back and just set it to the default of 5 to 20. The reason for that time span, there are a couple of factors that go into that, and okay, we're still set here to a very low rainfall depth, so let's pick our 10-year storm and click OK. So now we have a more reasonable hydrograph. Why does it go from 5 to 20? First of all, remember that this is the calculation window that we have set here. This is not the duration of our rainfall. Our rainfall is always starting at 0 hours, and in this case is running for 24 hours. Those are the settings on the rainfall tab, 24-hour duration. What we're seeing on this report is the calculation time span, which is the next tab. And this is where we have a starting time of 5 hours and an ending time of 20. It's also where the time increment is set, the calculation time increment. And that increment is independent of the increment that's used within your particular rainfall distribution. Those do not have to be the same value by any means. So the reason we default to starting at 5 hours is that in most cases there's little or no runoff before the 5-hour mark. This is a characteristic of the SCS runoff equation, and the fact that until we exceed the initial abstraction for our particular curve number, we're not going to get any runoff. And so that's why we have that set to 5 hours. If your curve number is quite high, such as a impervious surface with a curve number of 98, then you could actually start getting runoff before that 5-hour mark. So let's do that. Let's come back in and let's just put in 98. Of course, it doesn't match our description here, so it would be much better if we come into the table and pick one here. So now we've got a curve number of 98, and if you look closely at the curve, there is now some runoff occurring at the beginning of the curve. And so there is runoff earlier than the 5-hour mark, and we are now getting a hint, longer time span advised for full volumes. So this is telling us that portions of this hydrograph are actually being truncated, and some is being truncated before the 5-hour mark. That portion is quite important because all of that inflow might be accumulating in a pond, and so it affects our peak flow, peak elevation, and discharge from the pond. On the other hand, the runoff that's occurring after the 20-hour mark is usually after the peak has occurred, and so in most cases it doesn't affect our peak runoffs or our peak discharge from ponds. And so that's the reason we have a 20-hour mark at the end. There, of course, is no reason you can't change those values. So you can certainly go in and you can set your calculation time span to run from 0 to 24 or perhaps 0 to 30 hours. If you want to allow time to watch your ponds empty completely, then you will not only need to go to 24 hours but sometime beyond that. So you will want to look at your calculation time span, and in many cases you'll want to make adjustments to that. It will depend on the particular site you're modeling and on the objectives of your model as to whether or not you need to make that change. You'll notice the runoff depth is calculated and shown here at 4.26 inches, and one of the things I wanted to show you is that if we did bring that time span back to 20 hours so that we're truncating that hydrograph slightly, then the report now says that the runoff depth is greater than 4.06. What this means is it's taking the total volume over the calculation time span out to the 20-hour mark, and it's converting that to an equivalent depth of 4.06 inches. But the software sees that there is still a little bit of runoff occurring at the 20-hour mark, indicating that we're truncating that runoff, and that in fact the total runoff depth is somewhat greater than that value. So that's the reason that the greater than symbol appears there rather than an equal sign. And so if you want to get the total runoff depth in the report, then you want to bump that time span out a little bit longer so that everything is reported. So there are a number of issues that go around selecting that calculation time span, but keep in mind that that is different than the rainfall duration. And now I do want to comment on the rainfall duration. I skipped over that pretty quickly early on. Most storms you select, such as the Type 3 24-hour, have a built-in duration, which is often 24 hours. HydroCAD has the capability that you could change that duration, so you could rescale that duration to 12 hours. When you do that, the software is going to compress that storm so that rather than that distribution occurring over a 24-hour period, it's going to occur over just 12 hours. As a result of compressing by a factor of 2, our peak is going to be exaggerated by a factor of 2. So our runoff is going to go up dramatically in that situation. So this is to illustrate that in most cases you do not want to rescale storms to different durations. Most storms are intended for a particular duration and should always be used at that duration. If we have rescaled like this, then you will notice in your reports that it's going to indicate that this is a Type 3 24-hour, but that it's been rescaled to a 12-hour distribution, a duration. So that will show up in your reports. The better solution, if you feel you really need to use a different rainfall distribution, or excuse me, a different duration, then you should get the specific curve that's intended for that purpose. So go to our site, download the Type 2 24-hour rainfall. These storms are actually the middle 12 hours out of a 24-hour duration. So it's just discarding the first and last 6 hours and taking the center portion. So it will have exactly the same peak intensity at the center of the storm as the 24-hour distribution. And the same is true of the Type 2 6-hour. It's just a smaller window inside that storm, so you won't get exaggerated peaks when you use these. And these are starting to be used a little bit more, particularly for water quality storms, and that's the reason you'll now see that these shorter duration storms are automatically installed with HydroCAD. As always, it's a matter of your regulations and what they require you to use for your individual study, and this is different from one locality to another, from one state to another. Everyone's storm water regs are a little bit different, so you'll have to determine exactly what's suitable for your project. So that's essentially everything I wanted to cover as far as rainfall distributions. We've been through the different options for how you can set up your rainfalls, the different events, and what's coming with future versions. The other related topic to rainfall distributions that I want to touch on today are unit hydrographs. A unit hydrograph is often just ignored completely, and often it can be a confusing topic because it's just this mystery object that's there in the background when you're using the SCS runoff procedure. The unit hydrograph is set in your calculation settings on the unit hydrograph tab. In most cases, you're going to use the standard SCS unit hydrograph. And if you drop down the list, you'll see a couple of different unit hydrographs that are available to you. It's called a unit hydrograph because the unit hydrograph indicates the runoff that would occur for a short burst of rainfall, essentially 1 unit of rainfall. And it's a dimensionless unit hydrograph, so it's in many ways there's similarities to the standard rainfall distribution, but whereas the rainfall distribution is the temporal distribution of rainfall over time, the unit hydrograph represents the runoff, the flow rate for runoff from a small burst of rainfall. And if you go back into the HydroCAD manual and our other training materials, there's a detailed discussion of the NRCS runoff procedure and exactly what role the unit hydrograph plays. But what you run into in HydroCAD, where you need to deal with unit hydrographs, is when you deal with a different peak factor. The standard SCS or NRCS unit hydrograph, as you can see in HydroCAD, has a peak factor of 484. And this is a relationship between the peak of the curve to the total volume under the curve. There is also a K factor, which is another way that you can parameterize this shape of the curve. And if we click View Unit Hydrograph, it brings up the Unit Hydrograph report, which is very similar to the rainfall distribution report, but we're now looking at unit hydrographs. And the panel on the right shows you the different unit hydrographs that are available. The SCS unit hydrograph is certainly the most common with a peak factor of 484. The next most used is the Delmarva unit hydrograph. And this is used in the Delaware, Maryland, Virginia Peninsula, which is an area characterized by very flat slopes, among other things, very low slopes. And so it turns out that in that area, a unit hydrograph with a lower peak factor of 284 is better able to predict the runoff results for that area. So you can see graphically here those two unit hydrographs, and you can see the lower relative intensity for the Delmarva unit hydrograph. There are also different peak factors that are used in a few other locations in the country. This curve is the Southwest Florida Water Management District, and that has a peak factor of 256. So it's similar, close to the Delmarva, but not quite the same. And then there are also a number of unit hydrographs that were developed specifically in Georgia, and they actually have a 484 unit hydrograph that is similar to the SCS but not exactly the same. And then there's a 323 peak factor and a 300. And if you click the Edit button on any one of those, it'll bring you into the exact definition. And each of these has got a reference. So this one is from the Georgia Stormwater Management Manual, August 2001. So you can go back and check the original source. These Georgia distributions, by the way, are also used in Florida. And so we sometimes have requests for people who say, I need a 323 unit hydrograph for Florida. Well, chances are it's going to be the Georgia 323. If you run into an application that requests a different peak factor, then that basically means you need to use a different unit hydrograph. The peak factor cannot be directly entered into the software because it is not, the shape of the curve also needs to be specified. And so when you need to define a different peak factor, what you are actually doing is you're specifying a different unit hydrograph. There are a number of different ways you can actually generate unit hydrographs. There are different procedures. And so, again, a peak factor does not uniquely define the unit hydrograph. So if you have different peak factor needs, you can first go and look at the Delmarva unit hydrograph, which is the next most used, or you can look at our unit hydrograph download page on the website, and you'll find these additional distributions that can be downloaded from that site. You could have a brief look here at the effects of the different unit hydrographs. I guess let's leave this one at our curve number of 98, and if we have a peak now of 50 CFS, and if we change the unit hydrograph to the Delmarva and click OK, then that peak drops down to 34.9. So it is another factor that does affect our final runoff results. In most cases, you're going to be using the standard SCS unit hydrograph, so you won't have to change this. If you are working in a location where you're frequently or commonly using a different unit hydrograph, then that's another situation. You may want to use a default project in HydroCAD. A default project is a very useful technique. You can just create a project called default, and you can have a separate default project in each folder in which you're storing projects. You can also have a master default folder back in your HydroCAD program folder. So you just create a project called default, which is completely empty to start with, and we could now go into our rainfall settings, and perhaps we always want to use a Delmarva unit hydrograph, so we could choose that here and click OK. It also wants some kind of rainfall depth before it will accept this screen. And so now when we close and save this default project, anytime we create a new project in the same folder, that project will inherit all of the settings from default. In this case, the separate or the different Delmarva unit hydrograph. This default capability can be used to define any standard settings that you commonly use. So in addition to the Delmarva unit hydrograph, we might actually come in and import all of our rainfall events. If maybe this is a folder that is used for a particular county where the rainfall is the same or very similar throughout the county, so we could set up all the rainfall events as part of our default file. So there's a lot of different things you can do with a default file. The default can even have nodes in it. If you always want to have a particular subcatchment that you use as a template or a certain pond, then those could all be part of your default project. And then whenever you create a brand new project, it will make a copy of everything that's in your default folder and use that as the basis for the new project that you're creating. So that's the essential information that I wanted to cover today. If there are any other questions, you can put them into the chat or the question box. Certainly anything that comes up later, you can send them to support@hydrocad.net, and we'll be glad to get back to you. There are specific web pages on all of the topics that I've discussed today, and so we can point you to those best resources. And of course, if you go to the support page at hydrocad.net and scroll down there to the section on runoff issues, then you will find there a number of articles that talk about the rainfall distributions, unit hydrographs, and other topics. And down here under modeling issues, you'll find common runoff issues, rainfall, unit hydrograph selection, and the peak factor. So you'll find articles here that talk about all of these different topics. So I think, unless we have any other questions, we're going to wrap up a little bit early today. I do thank everyone for joining us. We do have another session in 2 weeks, which is going to dovetail with this, which will talk about related runoff issues and specifically about curve numbers and time of concentration. But you should now have a good handle on some of these behind-the-scenes issues. They're not as exciting, perhaps, or as immediate to you as a lot of the more current ongoing modeling issues you face, but these are critical topics because these are the foundations for the runoff methodology that you're using every day. So I thank you all for joining us, and hopefully we'll see you again in a couple of weeks. Have a good day. Bye-bye.